In this module, you will learn about thermal equilibrium and the zeroth law of thermodynamics. Before studying thermal equilibrium, we need to know what thermodynamics is. Thermodynamics is the study of exchange of heat and work between a system and its surroundings, and the resultant changes in the macroscopic variables of the said system. In thermodynamics, we deal with the macroscopic thermal properties of a system without knowing its internal structure. A thermodynamic system is an isolated body or a group of bodies with a well-defined boundary. It is important to identify the system, its surroundings, and the boundary that separates both of them. Some thermodynamic systems are as shown. Gas in a closed container is the system. The walls of the container act as the boundary. The environment acts as surroundings. Refrigerant is the system. The walls of the coil acts as the boundary. The compartment of the refrigerator acts as surroundings. The fuel inside an engine is the system. The walls of the engine are the boundary. Environment acts as surroundings. A thermodynamic system can exist in different states. The state of a thermodynamic system is identified by its macroscopic variables such as mass, pressure, volume, temperature, entropy, and enthalpy. For example, consider a given mass of gas at pressure P1, volume V1, and temperature T1. The state of a gas is identified by providing these values P1, V1, T1. If the gas is compressed, these values are changed to P2, V2, and T2. Then the new state is identified by P2, V2, T2. The state is said to be in equilibrium if there is no change in any of the macroscopic variables that distinguish the state with time. A system of gas in a container is said to be in equilibrium state if the pressure, volume, and temperature of the gas do not vary with time. The state of a system changes if the system exchanges heat with its surroundings, or when work is done by the system, or when work is done on the system. Whether a thermodynamic system can exchange heat energy with its surroundings or not depends on the nature of the boundary. An adiabatic wall does not allow any flow of heat through it, whereas a dithermic wall allows the flow of heat through it. That means an adiabatic wall acts like an insulating wall and a dithermic wall acts like a conducting wall. Consider a container with two chambers A and B separated by a partition. Take two gases in the two chambers, gas A and gas B. The state of a given mass of gas can be completely expressed by independent variables, pressure and volume. Let the initial state of the gas in container A be PA, VA, and that of the gas in container B be PB, VB, and the walls of the container and the partition between the chambers are adiabatic. As time passes, since the walls and the partition between the chambers are adiabatic, there will be no change in any of the macroscopic variables of either gas A or gas B. Let's retain the adiabatic wall as it is and replace the adiabatic partition with a diathermic material. Now, exchange of heat energy takes place between gas A and gas B, and as a result, there will be changes in their macroscopic variables. After sufficient time, they will settle at different equilibrium states, PA', VA' and PB', VB', and there will be no exchange of heat energy between them. We say that the two systems are in thermal equilibrium. Two systems, A and B, are said to be in thermal equilibrium when 1. They are in contact with each other or separated by a diathermic wall, and 2. The state of system A is in equilibrium with the state of system B. What will happen if we retain the adiabatic partition between the two chambers and replace the insulating walls with diathermic walls? After sufficient time, gas A and gas B will attain different equilibrium states. But as the walls are diathermic, gas A and gas B are in thermal equilibrium with the surroundings. If we replace the adiabatic partition between the two chambers with a diathermic partition, then there will be no flow of energy between gas A and gas B. Because when two systems, A and B, are individually in thermal equilibrium with a third system C, they are in thermal equilibrium with each other. This is known as the zeroth law of thermodynamics. Now, if we measure the temperature of all the three systems, we find all of them at the same temperature. This fact is used to define temperature. Temperature is the macroscopic variable that is equal for both systems when they are in thermal equilibrium. You have now reached the end of this module. In this module, you learned that thermodynamics is the study of exchange of heat and work between a system and its surroundings, and the resultant changes in the macroscopic variables of the said system. A thermodynamic system is an isolated body or a group of bodies with a well-defined boundary. The state of a system changes if the system exchanges heat with its surroundings, when work is done by the system or on the system. An adiabatic wall does not allow any flow of heat through it, whereas a diathermic wall allows flow of heat through it. Two systems, A and B, are said to be in thermal equilibrium when they are in contact with each other or separated by a diathermic wall, and the state of system A is in equilibrium with the state of system B. When two systems, A and B, are individually in thermal equilibrium with the third system C, they are in thermal equilibrium with each other. This is known as the zeroth law of thermodynamics.